Hi, hello. I looked up actually on Google Translate how to say hello, and it came back with hello. So, hello, good morning. I'm going to talk to you guys about reinforcement learning. Now, I am going to spend pretty much this talk giving you a very basic understanding of this. And the idea is to give you something to build off of. This is something that I typically tend to do. I've done it with machine learning, I've done it with deep learning, and for today, I'm going to do it with reinforcement learning. And I've already had a wonderful introduction by Madeline, so there's not really a lot more to say there outside of, I'll just add, I'm an advocate at Google now, and I am advocating for Google Cloud Platform as well as machine learning and AI, sometimes together, sometimes not. Today it's going to be focused more on AI machine learning space. Now, reinforcement learning, it's like it sounds. It's this idea that you are trying to, in essence, create, and this is specific to technology, you're trying to create a model using some type of reward to incentivize the model to learn. I mean, that's really what it is at its heart. So the reason why this has become such a popular topic in the space is that it is part of the machine learning ecosystem, and machine learning is used for pattern recognition and prediction. And if you need more information, if you haven't explored this before, there's a lot of great information out there, but I'm going forward with the assumption that you already have some understanding of machine learning. And if you've heard of deep learning, that is part of the machine learning ecosystem. So is reinforcement learning. Reinforcement learning sometimes goes hand in hand with deep learning, and sometimes it doesn't. Reinforcement learning is something that sounds very simple, but yet can be extremely difficult to implement. So that's why we're going to try to talk through it a little bit. Now, to give you some understanding about reinforcement learning, let me talk a little bit about some examples. And back in the early 90s, this game, TD-Gammon, was built out to try to beat humans, or at least play as good as humans in terms of backgammon. And it was great. It learned really well. What was fascinating was not the way it played against a human in terms of like whether it could beat a human or not. What is more interesting is when it identified these plays that were better plays to make that a human hadn't come up with, found new ways to play the game. Cut to last year, DeepMind created AlphaGo, and well, they didn't create it last year, but it played Lee Sedol last year, and this was a world champion in the game of Go. Go is a much more complex game than chess. And AlphaGo beat Lee Sedol. It was really fun to watch, actually, if you hadn't caught it. What was fascinating, again, was the plays that it made that a human would have said, I wouldn't make that kind of play, it seems like a loss, but it actually led to a greater win. Now, the challenge for reinforcement learning is that it's received a lot of attention because it's used in the game space. You've probably heard about ATARI if you've heard about reinforcement learning in general and how DeepMind's used it for ATARI, which I'm going to reference again later. So games, it's fun. Who doesn't want to play a game? And it's couldn't lend itself better to this type of algorithm that you want to explore. The reality is, games are a great space. It's a contained space to be able to explore this algorithm, to prove that it can actually work. So that's one value, or one key reason on why you would use it. It's much more condensed and contained. But the thing about it is that this has much more far-reaching applications. And so Google, we have used it to apply it in our data centers, and we were able to reduce our cooling energy use by 40%. That's huge. So when you can take a problem and define some type of reward, some type of goal, and give it the ability to explore the space, give that software the ability to explore the space and find an optimal way to work in this space, anything that you can do and try to convert into that format will allow you to apply reinforcement learning. Again, seems simple enough, right? The reality is that it is hard because you need a lot of data and a lot of time to make it work. But let's dive into what exactly this looks like. Let's get into a little bit more of the nitty-gritty. Now, when you work with reinforcement learning, there are some core components that you're working with. And let's see, my nice little pointer's not going to work for me here. But the two two key pieces in this is the environment and the agent. The environment is what you're exploring. The agent is what you get to control. That is your software. And in the environment, the agent can take it can be in certain states, like I'm standing in front of a door, and it has a certain number of actions that it will be able to take. Like I could open the door, I could turn and walk away. So it has states it exists in, it has actions it can take, it has new states it can move to. In the environment, you've got the reward that you're going after and the area that you're exploring. And another component that exists up here, and I don't have it actually listed, but I like to emphasize, is time. Horizon is another way that it's referred to. Time is crucial because sometimes you get the reward immediately. You know, I picked up the ball and then I get a reward for it. Whereas I have to jump over a hill, run through the dale, get to a treasure chest, open it up, and then I get a map. And that takes a number of steps and time to get to the reward and to get to where we're going. So, as I mentioned, the agent you get to control. The behaviors of the agent is what is key here. And the behaviors really are your policies, or it's what you want to do in terms of the tasks that you're going to perform in the state that you're in order to get to that reward. And the environment, whenever you hear anybody talk about reinforcement learning, they will say MDP, that's markup decision process. It's trying to find the reinforcement learning task that will get you to the Markov property. You know what that is, right? Some of you might. But the Markov property is ultimately saying, and I'm going to simplify this, like this talk, I'm doing this talk in, 45 minutes? There's so much that could be covered, and I am simplifying a lot of this. So there's more depth, there's more robustness. But roughly, the Markov property is saying, in this current state, I'm standing in front of the door, I don't need to know anything that happened before I got to that door to be able to make a decision on the next step to get to the reward. I just need to know about my current existing state. So that will be what I can use to help me predict the next step, to help me decide what to do next. Sometimes you don't know anything about your environment. You're left completely blank. And sometimes you have some understanding of the environment. You use things like the transition function, which will give you things like the probabilities of you moving from one state to the next. It is not your behavior, it's the environment itself that's dictating, maybe that door does not unlock, maybe I will not be able to open it because it is locked. And I don't have the key, so the probability of me opening that door is pretty much 0. So the potential for me to move from one state to the next is your transition function, and then your reward function. Those two come together to help really define what your environment will look like. And as I mentioned, the agent moves through states and actions, and so when you start to map it out, because it's good to map things out, really you start getting into a tree. Now I have an overly simplified tree here, but ultimately what I'm trying to showcase is that you're in a certain state, you take an action, you move to a new state. Sometimes you have the probability of moving to multiple different states. You know, you may end up falling asleep or, you know, falling through a hole. There's multiple states that could come out of one action. There's multiple actions that you have that could come into the next state. But what it looks like is, when you start to map it out, it can look like this huge graph. Now, I've used a min-max example in this case, but I'm trying to take this to another step to help you really fully understand what's happening here with states and actions. In the game of tic-tac-toe, I'm showing you kind of a current state, just we're peeking in where it's already being played, and then how it could look as you're playing against your opponent in terms of the next step you could take versus the next step they could take, and then where it would lead to in terms of subtype of result and reward. And you are basically going to take that and help you decide what path do you want to use to move forward. Now with tic-tac-toe, the state space alone is fairly decent, but not too big. You could hold this in memory. You could do the calculations to get to the reward in memory. Checkers has actually been fully mapped out, exhaustively searched, as they would say, where you have the full state space and action space mapped. You know what the rewards look like. You know how to get to the best path to win the game based on the positions that you're in. But when you start to go up the chain in terms of the size, the complexity of that game, that's where you are getting to a point where you cannot put it in memory fully. You cannot fully hold everything that you need and then also spend the time to quickly calculate what the rewards look like. It would take days, months, years, more than a lifetime in certain state spaces. The more complex, you are starting to get to a place where you cannot fully map it out. And when you hit continuous environments, there's just no way. That's where we get into these unique and different approaches to taking reinforcement learning algorithms to help you figure out good paths without having to fully exhaustively search everything. And as I said, reinforcement learning is about the goal, is about the reward. It's about getting to the best reward, the max reward. But what it really is, if you haven't already picked this up, is the optimal policy. It's finding the best behavior to move forward, to get to the end, to exit. You want to know, how do I behave? How does this agent behave to get to the max reward? And whenever you look at any of the algorithms that are out there for reinforcement learning, you'll see a star for optimal and pi for policy. I like throwing that in there just because I think it helps people start to kind of center on what is this actually translating to. Star gets used not just for policy. It's, you try to find optimal number of different optimalities throughout, but optimal policy is the end game, really. Okay. So, to do reinforcement learning, there's three main kind of functions that you're going to go after here. The model. Now, this gets a little confusing, I know, because I like to talk about models in general, and I do talk about the reinforcement learning model. But in this case, in this specific case, when I say model, when others say model, they're talking about the environment model. And it's the agent's, basically, perspective, mapping of the environment. The value function. The value function is a way to extrapolate out the reward function and apply it across the board throughout the various states that you can exist in, because you don't always get a reward in the current state or the new state you move to. And the policy. Sometimes you can model directly what your behaviors are going to look like. So those are kind of the three main areas that when you look at reinforcement learning, when people explore it, this is what they're trying to help you understand how to get to a good reinforcement learning model. You don't always do all three of them. Sometimes you do, sometimes you don't. Sometimes you do a mixture of some. Now, kind of to stress this point, as I mentioned, the agent, your current software, may try to track after the environment and keep a map of it of some sort. And it may already have information on the environment. It can take a number of different examples. I've just listed three, but the tabular form is where you usually start out with something very simple, something very contained. But when you start to get into like a Go game, you're not going to keep that in a table. And then the algorithms you use to figure out the best reinforcement learning model can sometimes be model-based or model-free, and meaning that you are tracking after your environment. And the value there is that with model-based, you're doing some level of planning. When you see anybody talk about planning and learning, you're planning, you're tracking what you've seen before, you're figuring out you went down this path in the maze before, so I shouldn't go back down that path anymore because it's not giving me the results I'm looking for. Model-based gives you information, but model-free allows you to have some level of freedom from assumptions and allows you to explore very complex environments more quickly. It can lead to complexities with being able to easily find an adequate model that would work for your optimal policy, but there's trade-offs. And there are people who would argue that it's great to throw the two together, to explore algorithms that give you more of a model-based approach versus a model-free, to actually do them both and then see what kind of information and compare notes. You'll actually see this as a common thing with reinforcement learning. There's a lot of like, here's an approach, here's a different approach. Why don't we just do both approaches and see what kind of results we get out of it? I'll bring this back up again later. So as I mentioned, this can go hand in hand. You can be doing some type of value function and or policy model. And when you start out, usually you don't have any information or you have very little information and you want to kind of just take a lot of random guesses. And you can spend a significant amount of time just randomly guessing. And you act, you're like, I am standing in front of the door, I think I'm going to open the door and see what happens, and I keep acting until I get experience from that action. And I can update my value function, I can update my policy model immediately, or I can learn from this and try to kind of draft this out in terms of what I think this looks like, and I can try to feed that back into my value function and policy model. I'll come back to this, but this is roughly where this plays out. So value function, whenever anybody starts out with the reinforcement learning space, they usually start out explaining value function. And as I mentioned, value function is about extrapolating the reward function and helping to provide some understanding of what the value is of your current existing state and the actions you're taking. When you work with reinforcement learning, you start out with the hello world, or you start out with the grid world, which is the hello world of reinforcement learning, from my perspective, from what I've seen. Now, grid world is a nice contained space. There's like 9 different states that you can exist in before you actually hit any kind of rewards. And in the grid world, there's an actual positive and negative reward. Doesn't always happen, but it's helpful to sort of explore it. Your action options in this case, depending on where you are, if there's a wall, of course you won't be able to go through the wall unless you got some magical powers, and that's suddenly a new part of the game. And there's the transition model, and this is arbitrary, but it's telling you in terms of the environment that the likelihood of you moving forward versus side to side is much more, in terms of within what the environment allows, is higher higher to move forward. So to figure out how to operate in this, to get to the reinforcement learning model, what they typically do for a value function is this cycling and iterating on prediction and control. And you're basically doing this kind of exploration, this start out random, trying a bunch of things, and then as you learn some things with your predictions, you're predicting this might be a good direction, then you do the control to say, okay, well, I've been through this multiple times now. I seem to be getting better results when I go right versus left, so I'm going to start to, when I'm in this state, go right and not necessarily left. For the prediction section, this is where the Bellman equation comes up. Whenever you look at value functions, usually you'll hear them talk about the Bellman equation, and there's variations off the Bellman equation that will pop up as you go through it. But ultimately, what the Bellman equation is advocating for is saying, okay, I want you to say, hey, while I'm standing here in front of the store, do I have any kind of reward? What's my current existing reward? Nothing? Okay. But if I act optimally throughout to get to the end game, then what do I roughly have as a reward discounted back into this existing state? So I predict that I'm going to go forward optimally and I'll get something out of it, and then I'm going to kind of roughly adjust and bring that back and say, even though my end game reward is 1, in the state standing in front of the door, it's going to be like 0.2 because that's the state you should be in to get in the right direction. You'll combine that will be your value function. And then, as I mentioned, with the control, you're just trying to say, give me the best move at this point that I've seen out of all the examples, all the times I've been through this position. And ultimately, you'll iterate over and over and over and over and over again for a really long time, and this is where the reinforcement learning problem or challenge comes up, is that you have to spend a significant amount of time exploring to really get any kind of results out of it. But once you've done it enough, and these are some arbitrary numbers to show you, you will eventually get some kind of information that will help you understand, hey, I'm in position 0, 0, let's turn in this direction, and actually, let me think, as we're facing this, technically, turn to the right. So this is the information you want to get to. You want to understand how to act optimally. And what you're seeing up here is an example of saying, I've ascribed a value per state. Now, value functions can break up into multiple kind of main sections, and I've got 4 listed up here just to give you an understanding of how this looks, and they're great to explain them from the standpoint of how much are you going to explore in terms of how much of the environment can you fully understand, and how far down the search tree will you go, and before you make any updates to your actual value function. In exhaustive search, you're going to fully explore all the states, you're going to make the updates accordingly, and that's not realistic when you get into very complex spaces, and I think you guys get that at this point. With dynamic programming, you're going to probably fully explore the space, you can fully explore the space, and you'll quickly make updates as you go. You won't go too far down the search tree, it may not even be that deep of a search tree to begin with. Monte Carlo is when you say, my space is too big to really fully explore, or it's great for when my space is too big to fully explore, and you'll do sampling. You'll do a lot of sampling, but you need an episodic environment, so you need some end to get a reward, so you can then feed that back. And TD learning, temporal difference learning, takes dynamic programming and Monte Carlo and puts them together, because like I said, we like to just say, hey, let's take a little bit of both and see what happens. And so it's taking this approach of saying, let's feedback the results without going too far down the tree, but let's just do sampling and see what we get. So with dynamic programming, the key thing to understand is that you are combining your probability of transition, the transition function that I showed you, with what the reward looks like and what the future discounted rewards look like. So it's your Bellman equation combined with the transition function. And all you're doing with the control is saying, okay, I've explored it, I've got this value function, I'm going to pick the best option. Something else to note is that I've stressed before about how you will have values per state. Well, with Q values, you're doing a value per state action. With Monte Carlo, you're sampling. You're basically saying, it's got to be episodic. I'm going to get a real result. I'm going to see what that result looks like at the end and decide based on what that real result looks like if I'm actually if I'm going in the right direction. And I'm going to keep doing this. It's kind of a frequency count to a degree. With temporal difference learning, as I mentioned, this is combining both dynamic programming and Monte Carlo, and this is where you find Q learning. So if you've heard of Q learning for reinforcement learning, it's coming from temporal difference learning. And specifically, and I'm going to say Q learning is about using Q values, and it's specifically saying, you know, we're going to do this immediate update, we're going to do sampling. The reason why temporal difference learning, and not necessarily just Q learning, but temporal difference learning is interesting, is that if you have an agent that's, let's say it's about to expire, it sees that it's going to run off a cliff, you don't want it to run off the cliff and then have to update itself. It's kind of pointless. You want it to update itself before it runs off the cliff. So temporal difference learning allows for that. And Q learning is saying we're exploring a space, updating a policy in real time, but it's not necessarily the policy that we are focused on and we're using. So that's an on-policy, off-policy differentiation. There's a couple of different algorithms you can explore in this space. Now, Q learning. Q learning is used in deep Q networks. And the difference here is, and it's not that much of a difference, you're just adding in a neural net, because everything's better with neural nets. You gotta throw in a little bit of neural net and you're good. With deep Q network, this was made by DeepMind to play the ATARI games. So if you've heard about the ATARI games in reinforcement learning and you've seen these, then you have been seeing what they've done with deep Q networks. Let's see, will this play? Because it looks like it's not loading. Oh, we love technology. All right. So I'm going to just explain, because it's not loading, unfortunately, that, you know, the ATARI games were, and there were a number of games that were used in the space to explore deep Q networks. They found that they were able to get significant results out of them to where the bots that were trained on these ATARI games were able to perform and successfully be beating what a human was able to do in these games. Oh, it's too bad this is not loading. Let me double check something real quick and see. We're going to do oh my God, the real thing behind the curtain. Let's see. All right, anybody got the password? It's live coding. Not really. It's not live coding at all. All right. Thank you. This is really nice of you. Ah, merci. Yeah, it's all right. Everybody should see this now. If you don't, password. BP Innovation Hub. BP Innovation Hub, by the way, if you didn't catch that. All right, great, we're up. Now, it doesn't matter as much with the, yes, you should probably keep that. You don't want to get kicked out. Okay. It doesn't matter as much with this video, but it actually matters for another video I have later, so I'm glad it's up and running. Anyway, so there's a number of them out there in terms of examples. You can find it on YouTube if you haven't already seen this, but I recommend checking them out there because it's fun. But you can see that this bot, you know, it's already been trained. It's fun when you watch them too when they're in the beginning because they die like really fast all the time. But this one has definitely been trained successfully so that it is, you know, doing a really good job avoiding getting killed and killing off all the other aliens. All right. So, just like Game of Thrones, I'm going to squeeze in the rest of this. because value functions, I've given you a nice overview. Value functions is sort of this popular space that was initially explored by reinforcement learning in terms of how to make this work. And then there was sort of this other direction that people went in, which was saying, hey, why don't we just directly model these policies? Like, why don't we come up with a model that will help us to determine what's the best behavior? Seems obvious. And then you ask yourself, okay, well, why didn't we do that to begin with? Well, you know, why don't we explore all the options? But with models, with policy modeling, the reason why you're doing this is, and I'm totally taking this from David Silver's talk that he's done. He's got some great videos out there. He had mentioned how, you know, if you look at the game Rochambeau or rock, paper, scissors, you're not going to have a reward value that you can ascribe to the different hand positions that's going to differentiate them. It's a uniform random policy. That is the model. That is the best model for that game. Now, there could probably be some nuances here, but I'm going with the simplistic approach here. Uniform random policy, that's a policy model. So it's great to use policy models, especially when you've got like continuous environments, and it's also helpful when you are trying to, you know, reduce the amount of storage you need to track. Because if you think about it, when you're trying to track a full search tree of all the states and actions and its corresponding rewards, it's helpful that you don't have to do that you don't have to do that level of computation to get to a policy model. So, so it's really good with high complex problems. And it does have a significant challenge from variance. It's very hard to get it to be repeatable in terms of seeing successful models. So they have a number of techniques like baseline and advantage function that are used to help you overcome this. As I said, I'm squeezing this in at the end. I'm not going to go through these algorithms. These are just a few of the policy model algorithms that you can explore. The main thing I want to stress is that they fall into two different groups, which is gradient and gradient free, or frequency, depending on how you look at it. But these are ways you can approach doing policy models. And of course, you can use a neural net, because everything's better with a neural net. I will take a second to say that Karpathy, who's a well-known researcher and leader in just machine learning, deep learning, reinforcement learning space, he did this nice example, I think a year or so back, and posted up a blog post about how to use a policy gradient model to win at Pong. Now, Pong was also explored with the DQN, but this is specifically showing you how to use a policy gradient model and combined with explicitly a neural net. Well, a policy gradient model is a neural net, but using the neural net. And what it looks like is you take the actual images, you break them down into pixels and the video images, and you convert those into numbers, and you feed them into, I believe it was a CNN, it should be a CNN because all images usually go through a CNN. And then you run the neural net to come back with saying, do I move my paddle up or down? That's your policy model. I'm moving the paddle. It goes up or down, direction, which way. I ran this on one of the servers that I have access to, and for the first couple days it was losing, totally dying. It was like, nah, not going to win at all. But by day 3 it actually started to show it could win a few games, which was really kind of inspiring. And by day 4 it was like winning almost all the time, and then by day 5 it died because it ran out of memory. But it was fun to play with. It's really easy. It's like a one-pager, so I'd recommend checking it out. And there's probably been various implementations off of it. And like I said, reinforcement learning, let's just, we've tried a couple things, let's just throw it all in the pot and see what comes out. So why don't we do value functions combined with policy models? Because in certain situations, it's not a bad idea. And so that's where you get this model, if you've heard about it, or this algorithm, if you've heard about it, called A3C, Asynchronous Advantage Actor-Critic. Sometimes you hear A2C, and that means they just lopped off the asynchronous part. But ultimately, what you're trying to do is you create this critic using something like temporal difference learning that will help you predict policies and help you evaluate policies. Now, actually, it's not predicting so much as it's evaluating. It's evaluating and it's estimating the value of what you've been doing. While your actor is the one that's saying, I'm going to do these policies, I'm modeling my policies, and I'm going to kind of go with these policies. And I'm going to combine what the value looks like from the critic with my scores on my policy model to help me determine the best direction to move in. So this is your actor-critic model. And the asynchronous part is, they were like, why are we just doing one agent, one environment? Why don't we just spin up a number of parallel, multiple copies of the environment, multiple copies of the agent, let them run, and then we'll combine the results later to pick which is the best tasks and policies to go with. And DeepMind, this is fairly old, but, or not that old. Everything seems old, like it's 2 days and it's old. But DeepMind explored this with a labyrinth, and the goal was this first player trying to find apples. The value that you get from models like this is you speed up the turnaround time, because that's, like I said, the challenge is data and time. Trying to have the amount of data that you need to fully train these models, because when you start out randomly exploring, it takes a lot of time to actually finally get some kind of signal. And so it takes a lot of time and data to get some type of signal. Okay, so what I've gone through, I've talked to you about how you are going to model your environment and use that to make plans. Sometimes you do, sometimes you don't. Sometimes you do both. You will get a value function to help you to take your reward and extrapolate it back over all your different states and actions. You can use something like dynamic programming or Monte Carlo or temporal difference-learning, depending on what makes sense based on the problem you're working with and the data you have available. You will do a policy model to help you search for the best policy to apply and figure out how to behave directly modeling that policy. And then if you want to combine the two together with value function and policy search, you can explore something like actor-critic models. And that's where we're at, right? We've got this value function, this policy model. You may or may not have both. You're going to take a lot of random guessing. You're going to act. You're going to get experience. You may directly update those, and/or you'll take that information, you'll store it, and you'll update your model accordingly, and you'll make plans. And that's how that comes together. The challenges: convergence, getting your model to give you getting the reinforcement learning model to help you understand that this is actually useful, getting any kind of signal out of the noise. The other challenge, and I talked about this early on, is having a reward that you can get some kind of signal out of in terms of how far down the path is the reward delayed. How long does it take for you to get a result? And there are a number of techniques that you can use to help get down that path. You know, I've already talked a little bit about a few of those, especially when you're doing like temporal difference learning and you're trying to do value functions. Exploration and exploitation is also a constant challenge, because if you create the search tree, if you think about the states and actions as search tree, even if it's continuous, how long do you explore before you say, you know, now it's time for me to pick this path? How long do I go until I cut off paths that I don't think will have any value? Because, you know, you look at something like the game of AlphaGo and you say, well, it had these really unique plays that you would have thought were losses, but ultimately led to a greater gain. So when do I cut that off? When do I say that this isn't worth my time anymore? How do I tell the software when to cut off? And this is a challenge that's constantly being debated in terms of how to further explore it. Generalization: when you've solved a problem, when you've been able to get a reinforcement learning model to work, then applying it to a new problem, a new, different approach, sometimes known as transfer learning. There's, in robotics, you know, I heard them explain this once where, you know, one problem they had solved was like the robot screwing on a top on a Coke bottle and then being able to apply it to something like screwing on a light bulb. You know, that is a great example of why it's useful to have models of your environment so that you can then think of, you know, this seems similar, so let me apply it to this other approach. But that generalization is hard. It's very hard in this space. And data's always a problem. Data's a problem because there's bias in the data. That's why I'm like, don't trust the data, because we as people, we are the ones collecting it, we influence it, we make it hard to make it useful. But data is a challenge, especially because you need it to be able to make these reinforcement learning algorithms work. Whether you are having it play multiple games against itself or not, you need to have the bandwidth, the systems, and the ability to run it for a long time so that it gets that kind of data that it needs to be able to get it to have an effect. And once it works, if you change anything, like if they were to change something small in the game of Go in terms of the rules, AlphaGo wouldn't quickly pick that up. Least it all would. Least it all would be like, okay, new rule, I will adapt to that. AlphaGo would need to spend a lot of time with new data to be able to figure out, this is the new rule, I need to incorporate it, and this is how I should be more strategic about it. So libraries that are great to explore in the space, these are just a few, and I've totally picked the ones that are from some well-known names out there, and these are a few that help you with, like, good examples of actual like ATARI games and other kinds of games that you can play with. I know that it's well known in terms of StarCraft is out there, and Doom are some games if you want to play around with some of the games. They also give you the algorithms themselves that you can play with in terms of how quickly spin them up and apply them. So like I said, these are just a few. If you go out and search, you will find others, and I'd recommend exploring them and trying them out. They're not that difficult to kick off. It's when you start to expand and dive deeper and solve problems that are harder that you start to hit up against some challenges. Okay, and this is the video I wanted to make sure would play. So I'll take a second.
Highlights from RoboCup 2017. And now, highlights from RoboCup 2017, vastly improved by Univision Deportes commentator Luis Omar Tapia.
El amarillo 4 quiere pasar entre medio de dos volantes del equipo azul. ¿Quiere? ¿Puede? No, señor. La pelota que rebota y está dividida en la zona media. Ahora va a venir el pelotazo largo, pero el balón que vino de primera. ¡Falta! El árbitro cobre la falta. Dejó seguir Ley de ventaja. El centro va a venir en el borde del área. Ya está al 5 para pegarle de zurda. Va a venir el martillazo. Le va a pegar gol.
Yeah, that was all me. I made that. So outside of the fact that I find this one fun to watch every time I watch it, and that it's a universal game, everybody loves football, I played this because a couple of reasons. Back in the early 90s, there was this professor who was the one who said, hey, I want to make robotics more approachable and get people interested in the advancements we're making in this space. Why don't we apply it to something interesting like, football? Because everything's better with games. And of course, we have to use games as a way to explore. In Japan, of course, the country of Japan, some of the researchers in Japan were like, this is a great idea. Like, let's actually do this. And then some other researchers in other countries got wind of it and were like, we want in. So in 1997, RoboCup was born. And you should go, if you haven't seen this before, you should go check out YouTube for some of the older videos. It's so much fun, and some of them are kind of weird in terms of the designs of the robots. These are definitely the cute robots that they've created. Somewhere down the line, reinforcement learning policy gradients were being explored. They were not the only thing, but they do play a role in terms of helping these robots play the game. And the goal of this group is to, they say right now they're trying for 2050, where these robots could actually beat a human player. I know, it seems kind of crazy when you watch these little bots run around, right? You're like, that's never going to happen. But people were saying that about, Go, and people were saying that about a number of things, and it's not impossible. When we see these advancements, that's what leads to the hype. That's what leads to us overestimating where this is going. It's great to see us achieve and get down a path that you're like, there's no way, or it feels really not possible and kind of feels weird. And then once we've gotten down that path, it's like people go, oh, we were able to play, Go? Well, we will now, solve world hunger, or, which would be actually great, but we will destroy worlds, which would be horrible. But it's kind of amazing how quickly everyone's like, and this is going to go crazy. And you're just like, no, let's just bring it back down to, let's try to solve this problem. So reinforcement learning easily lends itself to the hype. And there's excitement. There should be some excitement. And I always caution to temper that with pragmatic realism. Get excited, be inspired, drive after creating robots that can beat humans. That doesn't mean it's going to take away everybody's job. It just means we are going to get to some really sophisticated software. These robots will not know, and they don't know that they exist, let alone what really football means. They don't have any understanding. They don't have any real consciousness there. But getting to having this software that's complex, that can solve some real problems, can help us do some amazing things. I mean, if my company can reduce energy use by 40%, imagine the other impacts we can have when we have real problems like climate change out there. So, so there's a reason to be excited and inspired. Just try to rein it in a little in terms of how crazy you get in terms of where this could go. Okay. Last couple things I'm going to mention. So a couple things. One, I was mentioning about the challenges, some of the areas that are very interesting for those who are researching the space in terms of what they think they'll get further faster and more impact is in trying to find the better exploration versus exploitation trade-off, as well as I mentioned generalization or transfer learning, finding ways to take these models and apply them to problems without having to do as much to train them and to spend as much time with as much data. Bellman Equation, reinforcement learning in general, what it really is driving after is this idea that you have a big problem. Take that problem, break it into small chunks, solve those small chunks, and the overall solution will come from each of the chunks combines together to be the solution for the bigger problem. It's kind of true for a lot of problems out there, but breaking it down, solving smaller problems, combined together, ultimate solution. And optimal policy. I've said it before, I'll say it again, that's what you want. Yes, you want to maximize the reward, but what you want to get out of this is how do I behave to get to that reward? How do I get the software to behave to get to the best reward? That's the end game. These are resources that I have listed for, I think, good ones to start out if you're just exploring the space for the first time. And the Sutton and Bardo book actually gets mentioned a lot. Most of the actual training that I see out there sort of follows their methodology and breaks down most of their components to their initial approach. They've influenced everybody, basically. I used a lot of images. I had some friends who helped me put this together. And that was mostly what I wanted to cover for you guys. So thank you so much for taking the time to listen, and I'll take some questions, if there's time.
Thank you so much, Melanie. So we have some questions.
Great.
So I'm going to move us over this side just a little bit. We're going to
this
shimmy
way.
over.
All right.
Okay, so just a reminder to you all that we have Slido, and you can ask questions via Slido, and you can also feedback on talks via Slido. You just need to remember #CrunchBP. So, first question. In the absence of real test data, can generated, artificially created, data that closely reflects the real world be used as test data?
Yes. Yes, I mean, it's granted a large question, or a overarching question, and yes, typically you can use simulated data to solve problems. I mean, it depends. Everything always kind of depends on the problem and the data, but a lot of times you can use test data.
Okay, great. So can reinforced learning be used within recommended engines?
Reinforcement learning, sure. Actually, it probably has. I would need to do a search on that to confirm, but I suspect that it's already been explored in that case,
Okay.
yes.
All right, so let's see. Sometimes these change really quickly. So how did you get into machine learning?
I got into machine learning because I did what is known in the area that I live in, these boot camps, which you guys might have some here too. I did a boot camp on software engineering, and I did a boot camp on data science, and then I was very fortunate in some of the jobs that I ended up in, but I spent a lot of time studying and exploring and experimenting with data, with projects, and my starting out job when I finished up the boot camps was with Change.org, and I implemented like a recommender engine in production and a multi-arm bandit algorithm into production to help with some of our content that we were trying to emphasize. So that's how I got started.
Okay, great. So what is your favorite reinforcement learning project that you've been working at?
In terms of the favorite reinforcement learning project, I would say, this is something that is actually still a fairly new area for me that I've been exploring myself. So I've mostly been playing around with the games and exploring those games. In terms of what I've seen out there, I mean, I'm still, I'm actually still impressed by the energy improvement. I didn't work on that, but I was still really impressed by seeing that reduction in energy use, because I'm hopeful for where that will lead us. And the things that I've been hearing from various colleagues and friends of mine in terms of the work they're doing, and just in terms of utility use and improvements and optimizing operations around using reinforcement learning. So there's a lot of exploration that's still going on.
Okay, great. And so for our final question, you were saying do not trust the data and data is queen. Are you suggesting not trusting the queen?
Never. No. Queen never gives an opinion.
She's not dependable.
She doesn't give any opinions anyways. No, I
She doesn't have any real power anymore.
I know, right? No, you know, they kind of go up against each other, completely agree, but you have to have data. You have to have data to get results. You will get results, but you should never assume that what you have at the end of the day works exactly the way you expect, because it doesn't. You know, a lot of you guys I know are engineers. You know, you put something into the wild with your programs, and it's not going to work the way you expected. It always has some kind of glitch. So it's great to be vigilant, to understand that it's not going to be like you expect, and when it isn't, take it back, get more data, and work on it again. And think about what you might be doing with the data, what kind of data you have, and how you can improve upon that. But data really is important. It does rule the situation. That is where we're getting the most impact for our machine learning algorithms in general. And yes, the slides are actually on it's actually already out on my Twitter, but I'll retweet those so you guys can have those, and I know that the venue is going to be providing them.
Great. Thank you so much for your speech. Really appreciate it. We have a little present for you.
Wow.
Someone's been drawing. So this is all for you. Thank you so much for your speech. Have a great day.
Thank you.
Thank you.